Hello friends, I welcome you in lecture number 15 on series solution of differential equations. In this lecture we are going to discuss about Bessel's equation and Bessel's function. This Bessel's equation is very important equation of mathematics and we are going to solve this equation using Frobenius method. Sometimes they can ask you to write down Bessel's equation and its solution using Frobenius method. So first we understand what is Bessel's equation, then we will solve it using Frobenius method, and then we will discuss that Bessel's functions are nothing but particular solutions of Bessel's equation. So we start with the definition. If our differential equation is in this form, x square times y double dash plus x times y dash plus x square minus nu square y equal to 0. This nu is a parameter. We will read this as nu, nu. Pronunciation is nu. So nu is a non-negative real number, that is nu is any real number which is either 0 or positive, and for different nu's we will have different Bessel's equations. So this nu is called order of the Bessel's equation. So this type of ordinary differential equation, x square y double dash plus x y dash plus x square minus nu square y equal to 0, where nu is a non-negative real number, is known as Bessel's equation of order nu. For example, if we take nu equal to 0 here, then we will have Bessel's equation of order 0, which is x square y double dash plus x y dash plus x square times y equal to 0. If we take nu equal to 2, then we will obtain Bessel's equation of order 2. So in that sense, this nu is a parameter in this equation. We can take a value of nu as any non-negative real number, and for different values of nu we will have different Bessel's equation of order nu. Now we are going to discuss the solution of Bessel's equation with this arbitrary parameter nu using Frobenius method. And as we know, Frobenius method is applicable if we have regular singular point. So first we will show that x equal to 0 is a regular singular point of Bessel's equation, and therefore Bessel's equation has at least one solution in this form: sigma r x raised to r times sigma m equal to 0 to infinity am x raised to m. Instead of an x raised to n, we are going to consider dummy index as small m, because we will require another notation which will use this small n in this Bessel's equation. So first we prove that x equal to 0 is a regular singular point. For that we divide this equation number 1 by coefficient of y double dash, which is x square here. So to write down this equation in this standard form, y double dash plus py dash plus qy equal to 0, we divide equation number 1 by coefficient of y double dash, which is x square, and we will have y double dash plus this x divided by x square, that is 1 by x, plus x square minus nu square divided by x square. Now if we compare this equation with this equation, we find that p of x is 1 by x and q of x is x square minus nu square divided by x square. And now we multiply px by x and qx by x square. So x into px is equal to 1, x square times qx is equal to x square minus nu square. And these two functions are analytic everywhere because they are polynomials. Therefore both are analytic at x equal to 0, and therefore x equal to 0 is a regular singular point of equation number 1, which is Bessel's equation of order nu. Therefore by Frobenius method we can say that there exists at least one series solution of Bessel's equation in this form. y equal to x raised to r sigma am x raised to m equal to 0 to infinity, or this we can rewrite by taking x raised to r inside the summation, and we can rewrite in this form also, sigma am x raised to m plus r. Now as usual we have to find out y dash and y double dash. So I have written y dash taking derivative of x raised to m plus r as m plus r x raised to m plus r minus 1 am as it is. Then y double dash is derivative of this x raised to m plus r minus 1, this quantity as it is, m plus r am, this m plus r minus 1 times x raised to m plus r minus 1, that is x raised to m plus r minus 2. And we know that this y is solution of given equation, therefore it will satisfy this equation number 1. So now we can substitute y dash and y double dash in equation number 1. So I have written this, putting values of y dash, y double dash in 1. We have equation 1 is x square times y double dash, so that y double dash is here, plus x times y dash, this is y dash, plus x square minus nu square times y equal to 0. Now next step is we first make sure that in every summation power of x is m plus r. Here it is not m plus r, and here also it is not m plus r. So what we can do is we can first before checking for x raised to m plus r, first we have to multiply each of these terms with each of these summations. So first I have multiplied x square with this x raised to m plus r minus 2, and it is x raised to m plus r, these things as it is. Similarly, if I multiply this by x, here x to the power 1 and here x raised to m plus r minus 1, so we will have x raised to m plus r, and here we multiply this by x square first. So x square into x raised to m plus r, that is x raised to m plus r minus r plus 2 minus nu square into this summation, so that I have written here. So here now power is m plus r plus 2. In rest of the summations power is m plus r. So now I have to convert this summation in this type of power of x, that is in terms of x raised to m plus r. So for that we can see with r we have m plus 2, so we can change this dummy index m to new index say p by this variable, change of this variable m plus 2 equal to p. If I take m plus 2 equal to p, this will be x raised to p plus r, and m is starting from 0, so p will start from 2, and m plus 2 equal to p, that means m is p minus 2, so this m will be replaced by p minus 2, and instead of m equal to 0 to infinity we will have p equal to 2 to infinity a suffix p minus 2 x raised to p plus r, and rest of the summations are as it is. So that I have written here, sigma a p minus 2 x raised to p plus r. Rest of the summations are as it is, as in previous step. Now because this p is a dummy index, I can replace p by m in this summation. So in the next step I have done this work. I have changed this dummy index p to new index m, rest of the things as it is. Now what we have to do is we have to combine all these summations. So for that range of summation must be same. So you can see here range of summation is m equal to 2 to infinity. Here it is 0 to infinity, 0 to infinity and 0 to infinity. So what we can do is we can write down the terms corresponding to m equal to 0 and 1 for each of these summations, and then from m equal to 2 to infinity we can write in sigma notation. For example, for this summation first I will write down the term corresponding to m equal to 0. So that is r into r minus 1 a0 x raised to r. Then I will write down the term corresponding to m equal to 1, which is r plus 1, then r, and am, m is 1, that is a1 x raised to r plus 1, and plus sigma m equal to 2 to infinity, all these things as it is. Same thing I have to do for these three summations. This I will keep as it is. So you can see I have written the term corresponding to r equal to 0 for this summation, that is r minus 1 a0 x raised to r. For r equal to 1 I obtain this term plus sigma m equal to 2 to infinity, these things as it is. Same thing I have done for this summation. Term corresponding to m equal to 0 is r a0 x raised to r. Term corresponding to m equal to 1 is r plus 1 a1 x raised to r plus 1, and plus sigma m equal to 2 to infinity m plus r am x raised to m plus r. So that I have written here. Here summation is from 2 to infinity, so this I have written as it is. And then I have taken term corresponding to m equal to 0 and negative sign is there, so that is nu square a0 x raised to r. Then term corresponding to m equal to 1, which is nu square a1 x raised to r plus 1, and then sigma m equal to 2 to infinity, this thing as it is. So that I have written here. Nu square a0 x raised to r, nu square a1 x raised to r plus 1 minus sigma m equal to 2 to infinity nu square am x raised to m plus r. Then we combine the terms with power x raised to r. So here we have a0 x raised to r, and here we have a0 x raised to r. If I take a0 x raised to r common, I will have r minus 1 plus r into a0 x raised to r, and this term also contains a0 x raised to r, so minus nu square a0 x raised to r. Then we have combined the terms with a1 x raised to r plus 1 into r plus r plus 1, and this nu square a1 x raised to r plus 1. So r plus 1 into r plus r plus 1 minus nu square a1 x raised to r plus 1. Then sigma m equal to 2 to infinity, and coefficient of x raised to m plus r common. So this term m plus r minus 1 am, m plus r minus 1 am, then m plus r am. So that I have written here, and this am minus 2 minus nu square am minus 2 minus nu square am x raised to m plus r equal to 0, and summation is from m equal to 2 to infinity. Next step is, first we compare the coefficients of lowest power of x, which is x raised to r here. Right hand side is 0, that means coefficient of each power of x must be 0 for this equation to hold. So first I have compared coefficients of x raised to r, or I have written that equating coefficient of x raised to r in 2 to 0, that is this must be 0, that I have written here. Now whenever we assume Frobenius series solution, we start with the assumption that a0 is non-zero, and this is going to be r square minus r plus r, so r will cancel out, and we have r square minus nu square a0 equal to 0, and because of this assumption we must have r square minus nu square equal to 0. So whenever we assume our series solution, we should mention that where we consider or we assume that a0 is non-zero, and because a0 is non-zero, we have r square minus nu square equal to 0, and therefore r square equal to nu square, and therefore there are two possible values of r equal to nu and r equal to minus nu. These are the roots of initial equation, which is r square minus nu square equal to 0. Now what is this nu? Nu is a non-negative real number. Therefore there are two possibilities: either nu is an integer or nu is not an integer. So first we are going to discuss the case that this number nu is not an integer. So that means roots of initial equation do not differ by an integer. So first we will consider r equal to nu, and we will find out the solution of Bessel's equation corresponding to r equal to nu, where nu is not an integer. And before that we have to write down the recurrence relation by equating the coefficient of x raised to m plus r to 0, which is m plus r minus 1 am plus m plus r am plus m minus 2 minus nu square m equal to 0. So equating the coefficient of x raised to, before that we have to compare the coefficients of x raised to r plus 1 also. So I have written this is into a1 equal to 0. So equating the coefficient of x raised to r plus 1 to 0, we have r plus 1 r plus 1 minus nu square a1 equal to 0. If we simplify this, we have r square plus r, that is 2r plus 1 minus nu square a1 equal to 0. And now when r is equal to nu, that is we put r equal to nu in this equation, we have nu square plus 2 nu plus 1 minus nu square a1 equal to 0, and this nu square will cancel out, and we have 2 nu plus 1 into a1 equal to 0. Now because this product is 0, either a1 is 0 or 2 nu plus 1 equal to 0. Suppose 2 nu plus 1 equal to 0, then we will have nu equal to minus 1 by 2. But this is a contradiction. Why? Because in Bessel's equation we have this nu as non-negative real number. Nu cannot be negative, therefore nu equal to minus 1 by 2 is not possible. Therefore we must have a1 equal to 0. So here we have written that nu equal to minus 1 by 2 is not possible, as nu is non-negative real number. Therefore we must have a1 equal to 0 when r equal to nu. We are considering the case that root of initial equation is r equal to nu, and this nu is not an integer. Now after that we have to compare the coefficient of x raised to m plus r2 to 0, that is we will equate this bracket to 0, and let's see what we obtain. Equating the coefficient of x raised to m plus r to 0, we have this quantity which is coefficient of x raised to m plus r equal to 0, and summation is starting from m equal to 2 to infinity. Here m is from 2 to infinity, therefore we must have m greater than or equal to 2. This is valid for m equal to 2 to infinity. And in the next step I have taken this m plus r common. So here I have m plus r minus 1 and plus 1 and minus nu square am. This I have transferred on the right hand side, and now this is m plus r. This will get cancelled, and we have m plus r into m plus r, that is square of m plus r minus nu square am equal to minus am minus 2, m greater than or equal to 2. Therefore am equal to minus 1 divided by this quantity am minus 2, m greater than or equal to 2. And because we have taken r equal to nu, so if we take r equal to nu, we have this r equal to nu we will take later. Here this step is written by considering this minus sign multiplied with this denominator. So minus of m plus r square plus nu square am minus 2. This is recurrence relation. Now we have taken r equal to nu in this recurrence relation, and if I take r equal to nu here, I will have nu square minus m plus nu whole square am minus 2. Taking r equal to nu in this recurrence relation 3, we have this quantity, and then we expand this nu square plus 2 nu m plus m square. So we can see nu square will get cancelled, and we have minus 2 nu m minus m square am minus 2. And if we take this minus m common, we have 1 over 2 nu plus m am minus 2, m equal to 2, 3, 4 and so on. So this is the recurrence relation when we consider the root of initial equation as r equal to nu. And now we have written sum of the terms for m equal to 2, 3, 4 etc. If we take m equal to 2 here, we have a2 equal to minus m is 2 and 2 nu plus 2 a0, and this 2 I can take common, and I will have 2 square into nu plus 1 a0. Then if I take m equal to 3, then here I will have a3 equal to minus into something, and for m equal to 3 I will have a1, but a1 is 0, therefore a3 is also 0. Then we take m equal to 4, so we have a4 equal to 4 into 2 nu plus 4 and a2. So that I have written here, and in the next step I have taken 2 common, so I have 2 into nu plus 2, 4 is written as 2 square, and we have substituted value of a2, which is 1 upon 2 square nu plus 1 a0, that is written here. And this we can rewrite as, if I combine these two, I have 2 raised to 4, this is 2 can be written as 2 factorial nu plus 1 times nu plus 2 a0. So in general we can see here odd coefficients are 0 because a1 is 0, a3 is 0, and if a3 is 0, we can see that a5 will be 0. If I take m equal to 5 here, I will have a5 minus 2, that is a3, and if a3 is 0, a5 is 0. So in general am equal to 0 if m is odd integer. That means we have only even coefficients are non-zero, and here we can see a2 is 1 over 2 square nu plus 1 a0, a4 is 1 over 2 raised to 4 2 factorial nu plus 1 nu plus 2 a0. Okay, let me write a2 here. a2 was a0 divided by nu square into 2 square into nu plus 1. a4 is 1 over 2 raised to 4. Here I can write 1 factorial. a4 is 1 over 2 raised to 4 2 factorial nu plus 1 into nu plus 2. So you can see the pattern here. If I have a2 here, I have 2 square. If I have a4 here, I have 2 raised to 4. If I have a2 here I have 1 factorial and nu plus 1. If I have a4 here, I have nu plus 1 and nu plus 2. So we can assume the next term. If I have a4 here, then I can write down the next term. If I have a4, I have 2 raised to 4. So let me write 2 raised to 6 here. If I have a4 here, I have 2 factorial. That is 2 into 2 is 4. So here I will have 3 factorial because 3 into 2 is 6. If I have a4 here, I have nu plus 1, nu plus 2. So if I have a6 here, I will have nu plus 1, nu plus 2 into nu plus 3. So in general we can write down the general term corresponding to this. So what we can see here, here we have A2, A4, A6. So for that I can write this A suffix to M. Okay, and here if I want to write down for A suffix to M, suppose I have A4, then 4 means 2 into 2 and 6 means 3 into 2. Now if I have A4 here, I have 2 raised to 4. If I have A6 here, I have 2 raised to 6. So if I have A2M, then I will have 2 raised to 2M. Now if I have A4, I have 2 factorial. If I have A6, I have 3 factorial. So here I can write M factorial. You can see, if I take M equal to 1, I will have A2. That is, for A2 we have 1 factorial. If I have M equal to 2, I have A4, that is 2 factorial. If I take M equal to 3, I have A6, that is 3 factorial. And now we can see, if I have A4 here, 4 I can write as 2 into 2. Then I am going up to nu plus 2. If I have A6, then I can write 6 as 2 into 3. And here this product goes up to nu plus 3. So if I have A2M, then multiple of 2 is M. So this product will go up to nu plus M, nu plus 1, nu plus 2 and so on up to nu plus M. And M will start from 1, 2, 3 and so on. So here alternately positive and negative sign is there. Therefore we have to multiply by minus 1 to the power M. So in general we can write coefficients of our series solution in this form: A2M equal to minus 1 raised to M into A0, 2 raised to 2M into M factorial, nu plus 1, nu plus 2 and so on up to nu plus M. M takes the values 1, 2, 3 and so on. So this is the general form of coefficients in the series solution of Bessel's equation, and here these coefficients are 0 if M is odd, and if M is even they will be in this form. And here A0 is arbitrary, A0 is our choice, therefore they have taken A0 equal to 1 over 2 raised to nu into gamma plus 1. If you recall the definition of gamma function, then we know that gamma n is 0 to infinity e raised to minus x, x raised to n minus 1 dx, where n is greater than 0. So they are using this gamma function in the choice of this arbitrary constant A0. So they have taken A0 as 1 over 2 raised to nu times gamma plus 1. And recall these properties of gamma function also. Gamma n plus 1 is n gamma n if n is any positive real number. If n is integer, positive integer or natural number, then gamma n plus 1 is n factorial. If you are not familiar with gamma function, you can watch my lectures on gamma function in the playlist of beta and gamma functions. So here A0 is set as 1 over 2 raised to nu into gamma plus 1. Reason for choosing this A0 is to write down this growing product in some simple form. So if I take 1 over gamma plus 1, then I can combine this gamma plus 1 with this gamma plus 1 using this property, and we can rewrite nu plus 1 gamma nu plus 1 as gamma nu plus 1 gamma nu plus 1 as gamma nu plus 1 plus 1 using this property. If we have n gamma n, we have gamma n plus 1. Instead of n, we have nu plus 1. So we have gamma nu plus 1 plus 1, that is gamma nu plus 2. Now that gamma nu plus 2 can be combined with this nu plus 2, and that we will write as gamma nu plus 3. and so on. Finally, we will be able to write down this product as gamma function of nu plus m plus 1. So that is the reason for this choice of arbitrary constant a0. So in the next step, we are putting a0 equal to 1 over 2 raised to nu gamma nu plus 1. So that I have written here. a0 equal to 1 over 2 raised to nu. I have combined with 2 raised to 2m, that is 2 raised to 2m plus nu m factorial as it is. This is as it is, and this is gamma nu plus 1. Now in the next step, I combine these two, nu plus 1, gamma nu plus 1, and using this property, this I can rewrite as gamma nu plus 1, that is gamma nu plus 2. Rest of the things as it is. In the next step, I combine these two and I rewrite as gamma nu plus 3. And you can see last term is nu plus m, and by doing this process we will obtain gamma nu plus m at the last, and this I can rewrite as gamma nu plus m plus 1. So that I have written here. Rest of the things as it is. So these coefficients are further simplified in this nice form: a2m equal to minus 1 raised to m 2 raised to 2m plus nu m factorial gamma nu plus m plus 1 m equal to 1 2 3 and so on. And now we are able to write down first solution of Bessel's equation. We have assumed this form of solution: x raised to nu sigma m equal to 0 to infinity am x raised to m. Now we have seen that odd coefficients are 0. So now I have written here, we can write, instead of am x raised to m, we can write a2m x raised to 2m, because am equal to 0 for m equal to 1, 3, 5 and so on. We have seen that a1 is 0, therefore a3 is 0, and therefore all the coefficients with odd suffix are 0. This I can rewrite as, I am considering the term corresponding to m equal to 0, which is a0 x raised to 0, that is a0 into x raised to nu plus x raised to nu into sigma m equal to 1 to infinity a2m x raised to 2m. I have splitted this into two terms, as I have written this summation as addition of these two sums, because our formula for a2m starts from m equal to 1, 2, 3 and so on. Therefore I have rewritten in this way. In the next step, I substitute value of this a2m here and I obtain this term. And if we start this summation from m equal to 0, then we will obtain this term. For example, if I take m equal to 0 here, then x raised to nu as it is. For m equal to 0, minus 1 raised to 0 is 1, x raised to 0 is 1, 2 raised to m equal to 0, that is 2 raised to 0 is 2 raised to nu 0 factorial, and for m equal to 0 we have nu gamma nu plus 1, and 1 over 2 raised to nu gamma nu plus 1 is a0. So you can see, if I take m equal to 0 here, then also I obtain x raised to nu into a0. Therefore I can again combine these two and I can write down my summation as starting from m equal to 0 to infinity. So let me write here, this is from m equal to 0 to infinity, and this y1 is the first solution of Bessel's equation, and we have to remember this formula. This is special type of function. It is the solution of Bessel's equation. We have taken particular value of a0 and we have written this solution. Therefore it is called particular solution of Bessel's equation, and this nu is called order of Bessel's equation. And because this y1 is a function of x, and because it is a solution of Bessel's equation of order nu, it is called Bessel's function of the first kind of order nu. Remember, this y1 equal to x raised to nu sigma m equal to 0 to infinity minus 1 raised to m x raised to 2m over 2 raised to 2m plus nu m factorial gamma nu plus m plus 1 is known as Bessel's function of the first kind of order nu. You have to remember this definition of Bessel's function. They can ask you to write down the Bessel's function of the first kind of order nu or of any order. Here we have assumed that this nu is a non-negative real number, and we have written this solution by the assumption that nu is not an integer. If nu is an integer, then we will discuss in the upcoming lecture. And remember the notation for this Bessel's function of the first kind. It is denoted by j suffix nu, and because it is a function of x, we write x in the bracket. J of x suffix nu. Nu specifies the order of Bessel's function of the first kind. So therefore j nu x can be written as x raised to nu times, or we can combine x raised to nu with this power. If we take this inside the summation, we have x raised to 2m into x raised to nu, that is x raised to 2m plus nu minus 1 raised to m 2 raised to 2m plus nu m factorial gamma nu plus m plus 1 is called Bessel's function of the first kind of order nu. If we further combine these two, here power of x is 2m plus nu, here power of 2 is 2m plus nu, so we can rewrite in this form also, x by 2 raised to 2m plus nu, so that we can easily remember. And all we have to remember is minus 1 raised to m divided by m factorial gamma nu plus m plus 1 into x by 2 to the power 2m plus nu. And this Bessel's function is the solution of Bessel's equation when root of initial equation is r equal to nu, where nu is not an integer. Now if instead of r equal to nu, if we take r equal to minus nu, then the corresponding solution can be written by replacing nu by minus nu in this formula. So we have second solution, because these two nu and minus nu are not an integer. We have the case of roots of initial equation not differing by an integer, and we know that if roots of initial equation do not differ by an integer, then we can write down both the solutions in this form corresponding to both the roots of initial equation. So second solution can be written by replacing nu by minus nu in this formula, and notation is also j minus nu x equal to, here if I take x raised to nu here, then I will have x raised to minus nu sigma m equal to 0 to infinity minus 1 raised to m x raised to 2m. Instead of 2m plus nu, we have 2m minus nu m factorial. Instead of nu, we have m minus nu plus 1. And we can say that, or we can verify or check that nu is not an integer. Therefore, these two solutions, j nu x and j minus nu x, are linearly independent functions, and therefore we can take their linear combination to write down the general solution of Bessel's equation, which is y equal to c1 into Bessel's function of order nu plus c2 into Bessel's function of order minus nu. So we have written the general solution of Bessel's equation when root of initial equation, which is r equal to nu, is not an integer, and another root is r equal to minus nu. Because of this assumption, roots of initial equation do not differ by an integer, and we have seen that the solution corresponding to r equal to nu gives us the formula of special function, which is called Bessel's function of order nu, and it is given by minus 1 raised to m divided by m factorial gamma nu plus m plus 1 x divided by 2 to the power 2m plus nu. And you have to remember this formula. This is Bessel's function of order nu. Some authors are using another symbol instead of nu. They are writing p also. So that is also valid. It is just the matter of notation. If you wish, you can write in terms of small p also. Just replace nu by small p. M factorial gamma nu plus m plus 1 x divided by 2 raised to 2m plus p. This is called Bessel's function of order p, or this is called Bessel's function of order nu. So in upcoming lectures, our focus will be on Bessel's function of the first kind. We will see the problems related to Bessel's function of first kind in upcoming lectures. And in this lecture, we have obtained the general solution of Bessel's equation under the assumption that, or we have taken the case that nu is not an integer. In next lecture, we will see questions related to Bessel's function of order nu, and we will write down the Bessel's function in the case that nu is an integer. If nu is an integer, then how this Bessel's function will look, and for that we will use the properties of gamma function also. For now I stop here. We will continue in upcoming lecture. Thanks for watching.